The last part of section 6.2 talks about how to calculate the mean and standard deviation of a binomial probability distribution. In the chapter 6 slides, after all these notes and details, there are a couple examples similar to the one in the previous video. In fact, this one is also worked out in the lecture notes, but there are other examples similar to it, and I encourage you to give them a try. And then when you go past those, it gives the formula for the mean, or also called the expected value of a binomial distribution. And then after that, it includes some examples and other notes. But like before, I'm going to go right to an example. The mean and standard deviation of a binomial probability distribution can be found using the same formulas as in 6.1. These formulas can be used for any for any discrete probability distribution, including binomial. So that always works, but it turns out that for a binomial distribution, there's a simpler way to find the mean and standard deviation, and it's these formulas. These are also contained in the book and in the slides. So here's the mean and the standard deviation. And the example that we'll look at is number 43, 6.2, number 43. And according to this website, American Airlines flights from Dallas to Chicago are on time 80% of the time. And they say, suppose that 100 flights are randomly selected. So what they mean is that there is probably a big database of flights that have already happened, and from that database we'll select at random 100 flights that already took place. Part A says compute the mean and standard deviation of the random variable x, which is the number of on-time flights if the trial is 100. So we want to find the mean and the standard deviation. And to put this in context again, we'll take a look at what that distribution would look like. So this is similar to in the other videos, except this is going to represent the number of on-time flights. X represents the number of on-time flights. And let's see, the n here are our sample sizes. They want us to have our 100. So sample sizes of 100. And so this is what the histogram looks like. It has a pretty nice bell shape to it as well, and that's going to be important to keep in mind. The mean is going to be somewhere right in the middle. And if we were just to look at this and estimate, it seems like the middle is around 78, 80, 81, right around there. And then the standard deviations are just like what we did in chapter 3. And we'll find that using the formulas. So we use these formulas. The mean is just n times p. The n is the sample size, which is 100. And the p is whatever your percentage is. 80% are on time. So that's our probability of success. So I'm going to do 100 times 0.80, and that's going to be 80. 80 on-time flights. The standard deviation is this formula. We're just plugging in n and p, so that's going to be 100 times 0.80 times 1 minus 0.80. And when you plug that all in and work that out, it comes out to 4. So 4 on-time flights. So there's our mean, and there's our standard deviation. Part B of the problem says interpret the mean. And when you interpret the mean, you want to interpret it as an expectation. You could say something like, in a sample, or in a random sample of 100 flights, we expect to find, on average, 80 on-time flights. And I guess the key here is that word expect, and another important key is just mentioning the sample size, because that mean, the 80, it depends on what our sample size is. If our sample size was 200 and you plug it in, it would have been 160. So you want to put it in context and mention how big your sample size is. Part C of the problem says, would it be unusual to observe 75 or fewer on-time flights in a random sample of 100 flights from Dallas to Chicago, and why? One way to check to see if something is unusual is to find its position on the probability histogram. So let's take a look back at this histogram. From chapter 3, the empirical rule said that if your distribution is bell-shaped, that means that within one standard deviation is 68%, within 2 standard deviations is 95% of the data. And by tradition, any value that's more than 2 deviations away in these small tails is considered unusual. So all of these small values over here would be very unusual outcomes. And these values over here would also be very unusual outcomes. The first thing to do before we can even think about that is just to make sure that the distribution is approximately bell-shaped. And to check that, we can use a particular formula that can make that conclusion. You want to check to see if n times p times 1 minus p is greater than 10. So I'll plug in those numbers, 100 times 0.80 times 1 minus 0.80. It comes out to 16, and yeah, that is more than 10. So because that's more than 10, that means that this distribution is approximately bell-shaped. It's not a perfect bell shape, but it's very close. So now that we know it is a bell shape, it helps to draw out the curve and label the mean and the standard deviations. So I'm going to do my best to try to draw out this bell-shaped curve. So it looks a little bit like that, trying to replicate how it looks on that graph. We know that the mean is 80. We just calculated that. We know that the standard deviation is 4. So I'm going to measure out deviations going above and below. So this will be 84, this will be 88, this is 92, down here that's 76, 72, 68. But our criteria is that if anything is more than 2 deviations away, either past 72 or past 88, then it's considered unusual. So I'll just put this is unusual. So in either tail, if an outcome falls in there, that would be unusual. And so in these notes, it's just explaining that we're using the empirical rule. And just making a note that our cutoffs for the middle 95% are between 72 and 88. That's here and here. And again, as I mentioned, any outcome that is more than 2 deviations away is considered unusual. Any outcome that is within 2 deviations is considered not unusual. The question was, would it be unusual to observe 75 or fewer on-time flights? 75, so we'll want to go to the curve and see if 75 is in those tails. But 75 is, it's not. 75 is about here. So about here is where 75 is. And that would be considered not unusual. Whoops. Not unusual. And that's our conclusion. Since 75 is within 2 standard deviations of the mean, this outcome is not unusual. Alright. The next video is going to be on Chapter 7, and we'll go on to Section 7.1.